Let's consider convergence series. Let S be A0 plus A1 plus A2 plus and so on, which is sigma notation AI I from 0 to infinity, be a convergence series. So we'll assume that the whole series is converges to S. Then if we look at the partial sums, in particular we'll look at the partial sum at two consecutive partial sums. Say, if you look at Sn minus 1, that is a partial sum with the last term to be an minus 1. And if we look at the next partial sum, Sn, that is going to be a0 plus an minus 1 plus an. So what you notice from here is that Sn is your previous partial sum, which is Sn minus 1, plus the next missing term. So from here we conclude that Sn minus Sn minus 1 equals to an. That's the first observation. Second observation is, if we take limit of both sides, if we take limit of both sides when n is approaching infinity, and if we look to what is happening on the left side, if you look what is happening on the left side, then we're going to get limit of Sn, and n is approaching infinity. So limit of partial sum is going to be S. Limit of Sn minus 1, limit of partial sum when n is approaching infinity, we're going to get that expression on infinite sum at the end, so we're going to get S again. So on the left side, you're going to get S minus S, and we keep the right side, limit of n, and that is n approaching infinity. And S minus S is 0, so we got 0 equals to limit of an when n is approaching infinity. So to summarize, what we got is following. If we have convergence series, then limit of an equals to 0. If series converges, then it must require that limit of an must be equal to 0. So from here we got the divergence test. What if limit of an is not equal to 0? The divergence test. If limit of an is not equal to 0, then corresponding series is divergent. Notice that if the divergence test doesn't tell you anything about what happening if limit equals to 0. If limit over an equals to 0, then we might have series convergent, or we might have a divergence. So that divergence test doesn't check for that. It tells you what is happening if limit of a term an is not equal to 0. If limit is not equal to 0, then the series is divergent. For example, if you look at the series which consists of n from 0 to infinity, n plus 1 over 3n plus 2. In this case, an equals to n plus 1 over 3n plus 2. And we can easily take limit of that expression. I will use the rule of thumb to evaluate this limit. And I'm going to get n over 3n. And I'm going to get 1/3. Now I can use the divergence test, because 1/3 is not equal to 0. So, because limit of an equals to 1/3 and is not equals to 0, we can conclude that the corresponding series is divergent by divergence test. I'm going to be calling divergence test VT. Here we have series n plus 1 over n squared plus 3 n from 1 infinity. Use divergence test to see if it is convergent. So we want to apply divergence test with series to see if it converges or diverges. Let's try. So in this case, an equals to n plus 1 over n squared plus 3. We take limit of n I'll do rule of thumb. Then I have n over n squared, limit as n approaching infinity. I will reduce that expression. So we have limit 1 over n as n approaching infinity, and 1 over infinity is 0. So we concluded that limit of an equals to 0 when n is approaching infinity. Limit of an equals to 0. Therefore, divergence test is inconclusive. Divergence test will give us any information about the series only when limit of a term does not equal to 0. If limit equals to 0, it cannot give us any